So today we're covering glycolysis up to regulation. I'm not sure if I'll have enough time for gluconeogenesis, but I will try my best to cover that. But for now, I'll focus on glycolysis. One thing to note, oops, going wrong side. I know when you guys look at pathways like this, when you watch Vander Heiden's lecture, it might be very overwhelming to look at a lot of structures and a lot of enzymes. And I want to just first say that you don't need to memorize the structure. When I say fructose 1,6-bisphosphate, we don't normally expect you to just immediately look at this image on top of your head. So I would not worry too much about remembering the names. Unless maybe you're taking the MCAT, then maybe you do need to memorize those names. But for us, what we care about when we teach this is a couple things. One is that you understand general classes of enzymes. And so what I'm doing here on the screen, which I hope you guys can see, is I'm highlighting the key names of the enzyme. And I know every enzyme has a different name, but what I'm highlighting is that as much as all of these enzymes are differently named, they're all the same classes. It's a kinase, it's an isomerase, it's an aldolase, and so on. And so what I want you to kind of remember as I go through all of these steps is how it's almost the same mechanism, just at a different step, hence there's a different name, but the enzyme stays the same. So that's the first thing I want to emphasize whenever I'm teaching a new pathway. The second thing is you want to understand what are the things that come out and come in. And so specifically for glycolysis, it is these kind of parts. When does the ATP come in? When does the ATP come out? Those kinds of things is what you want to also understand. And lastly, I know organic chemistry is a prerequisite for this course, but what I want you guys to kind of just have an idea of is understanding if I look at one step to the next step, what are the changes? And so being able to kind of understand organically what happened can help you understand it. Do you need to memorize this on top of your head? No, I still kind of don't memorize it at all, even though I've seen this class for multiple years. But what's most important is that you guys can understand the pattern. So that being said, I'm going through one step at a time. And this, my PowerPoint will have all the mechanisms, so you guys can refer back to it in the future. I don't expect you guys to know and understand all the mechanisms after this recitation, but I at least hope that I can explain why it makes sense. So in the future, when you rewatch it, you guys can understand it. So the first step is this part right here, where we go from normal glucose to this next product right here. And the first thing you should notice is that the only difference is a phosphate was added. And you guys remember the classes of enzymes that add phosphates are kinases. So in this case, the particular kinase is called hexokinase. In this case, anytime you see a kind of enzyme and you see a phosphate added to it, you should expect it's a kinase that does that. And so in this case, the hexo is less important. For us, maybe if you do say hexokinase, it tells us that you know the pathway. But if you just mention kinase, it allows us to understand that you know what kind of biochemistry is going on. So that's the first step. And with regards to that, the pathway mechanism is almost the same as it's pretty much the same as the mechanism from Yaffe's half when he talked about phosphorylation. So the trigonal bipyrimidal metaphosphate intermediate, basically that pathway is the intermediate that occurs when you do this reaction where you add a phosphate to glucose. And the whole point of this reaction in terms of why this reaction matters is that the first thing is that when you attach a phosphate group to glucose, you turn it from something that is relatively neutral, like this group right here, to now something that's negative. And because glucose is now negative, the result is that it is trapped inside the cell. So once glucose is now negative because it's attached into a phosphate group, it cannot leave the cell anymore. And so this is also a way for us to make sure that glucose stays inside the cell. And one thing to also note is that this step consumes ATP. And so as a result, we actually don't get any energy from this step. We actually spend energy on this step. And so this is part of the so-called investment phase of glycolysis, where if we look at the next slide, or the last slide, this first half is all about us putting in ATP or investing energy. And then the second half is where we harvest that energy. And so first step is just phosphorylating the glucose. The next step, let's look at it like what's the different part. In this case, we turn glucose 6-phosphate into fructose 6-phosphate. The change is not so obvious at first. The one thing that you guys might notice is that it goes from a hexagon to a pentagon. And so one thing to note is that it might not obvious in the ring form, but basically glucose is an aldose, whereas fructose is a ketose. And so this, oops, sorry, you can ignore that. For the sake of this reaction, the aldose to ketose is a relatively straightforward reaction. Basically, we're turning one isomer into the other. And so as a result, the enzyme we need for that is isomerase. And so for isomerase reactions, we've kind of seen them in Banner-Heiden's first lecture, but it basically occurs on this mechanism. And so to kind of understand how that mechanism works, we can kind of look at it here. We turn glucose into a linear sugar. So we can clearly see that once it turns linear, that we have an aldose because it's an aldehyde. And then in order to turn it into a ketose, which is this sugar, what we do is we get rid of a hydrogen first to generate the so-called cis-enediol intermediate. And then after we generate the cis-enediol intermediate, we add back that hydrogen that we lost to generate a ketone. The exact arrow pushing mechanism is not like a super specific thing that we ask you like organic chemistry, but if they do ask you to draw, I don't know how they can do it on an MITx format, but if they do ask you how this mechanism happens, it'd be important to remember that the cis-enediol step exists as the intermediate for this step. One thing to note is that regardless of what kind of sugar you have, the mechanism stays the same, as in even if this is a longer sugar or a shorter sugar, if you're doing an isomerase mechanism, then you're still using the same mechanism. And also note that even though this step is an aldose to a ketose, we can also turn this reaction backwards. And so you can also generate a aldose from a ketose. And so this is just something to keep in mind. And all this reactions we're going to see in the future, where we go from an aldose to a ketose or ketose to aldose, you should think of this mechanism, or at least know that this mechanism is the one in play. Now we've done with 2 steps, and one thing to note is this first step, you should notice that the arrow is single-headed, whereas in the second step, the arrow is double-headed. And so one thing to note from that is that when the arrow is single-headed, you might remember that this is an irreversible reaction, whereas a double-headed arrow is a reversible reaction. And the reason why the first step is irreversible is because ATP was consumed. Because ATP was consumed, the result is that the delta G becomes very negative. And when we have a very negative delta G, we pretty much say that that is a very irreversible step. But for the isomerase reaction, I didn't show the delta G here, but the delta G is relatively close to 0. So in this case, we would consider that relatively reversible. So you want to observe the changes in the double-headed arrow and single-headed arrow as well. Okay. The next part, we want to go from fructose 6-phosphate to fructose 1,6-bisphosphate. In this case, the only thing that changed, we add a phosphate. And so I hope that at this point you're already thinking kinase, and it is a kinase, phosphofructokinase 1. you might want to write down the enzyme names just for reference, but you should be able to just say, okay, it's a kinase mechanism, pentavalent metaphosphate. So whatever we learned from Yaffe is the mechanism for that. Now you have fructose 1,6-bisphosphate, which is normally shortened as F16BP. We go from F16BP to now 2 sugars. And this is probably, in my opinion, the most complicated step in glycolysis, where you go from this 6-carbon sugar into 3 carbon sugars, 2 3-carbon sugars. And so this specific enzyme that we haven't talked about yet is called an aldolase. And so to kind of show you what the mechanism of that looks like, I have the aldolase slide right here. So for aldolase, essentially the way the mechanism works is you start with a 6-carbon sugar, which in this case is F16BP. And through these series of arrow pushing, we basically kick out a 3-carbon group first, and then we kick out another 3-carbon group second. I'm going to go over the mechanism, but if you do not understand it too much in depth, you can just make sure to have it nicely written on the cheat sheet. But essentially, the enzyme, through a lysine, attacks the carbonyl of the sugar. And when you form that, you generate an alcohol. So the first step is nucleophilic attack. And then the next part is we actually get rid of water. So water elimination. So that's why we have this part right here. This electron pushing right here where the base takes the proton and the OH leaves. This is a dehydration step. One thing to note is that you're probably looking at this and saying, whoa, an OH minus group just left. And I remember from 512 that is a bad thing to have. Actually, in biochemistry, we can write this mechanism this way. So you can kind of like just say that this is normally how we write it down. But for us, because this is an enzyme environment, this could be possible. Then after the water was removed, we can have a reaction where we can actually get rid of the first part of the sugar, this first group right here. And in this aldolase mechanism, it's always the aldose that comes out first. So if you look at this first product, the first product is an aldehyde containing sugar. So we would say that the aldose is released first. After the aldose is released, you generate an enol, and then water can nucleophilically attack to break that and basically break this bond by attacking it. And the result is you get the ketose. So the ketose leaves next. And so it's unlikely that you're going to be asked to rewrite this mechanism again because of the limitations of MITx. But they might ask you a typical question where it would be, if I have an aldose mechanism, what is the first sugar that comes off first? And so you might need to remember that aldose comes out first and then the ketose comes out next. For those of you guys who are watching this, if you are having a hard time kind of writing down everything, I posted the PDF of this also online. So feel free to download that and then annotate whatever I write on screen. So hopefully that is much easier than copying everything down. For those of you who are live right now, do you guys have any questions? Okay, so we are now in this part where we have 2 sugars. So in glycolysis, it's only the glyceraldehyde 3-phosphate that can actually move on to the next step. And so we need to somehow convert this other sugar, which is called dihydroxyacetone phosphate, also shorthanded as DHAP. We need to find a way to transfer it and turn it into glyceraldehyde 3-phosphate. What you should be thinking right now is, what's the difference between the two? And the difference is that this is an aldose and this is a ketose. And so hopefully by now you've seen this reaction already. Turning an aldose into a ketose is simply an isomerase reaction. So you should imagine in your head that this enzyme is an isomerase. And you're exactly right if you did think that, because the enzyme is called triose phosphate isomerase.